All right, ladies and gentlemen, my name is Glenn Sizemore. I am a senior technical marketing architect here at VMware in our storage and availability business unit, and I am responsible for all things storage in the VMware Cloud on AWS service. This morning, what I'd like to do is quickly walk you through what the storage architecture looks like for us inside the VMC service and answer any questions you may have about consuming it. First things first, though, we need to know what kind of problem you're trying to solve, right? Because we've got a pretty powerful set of options inside the service. If we're dealing with a standard environment, of course, we can deploy one of our standard multi-host clusters. This is going to land all of the vSphere hosts inside a single Amazon region, inside a single Amazon availability zone. This, of course, means that if that AZ were to suffer a catastrophic failure of any sort, the cluster would be exposed to that. For workloads that just can't tolerate that level of exposure and require a infrastructure level solution to the AWS availability problem, we make stretch clusters available. And that's an add-on to the service which adds on vSAN stretch clustering, introducing that metro storage solution where we're going to synchronously replicate the storage when designated via policy across multiple AZs, guaranteeing that the loss of an entire Amazon availability zone becomes a standard HA restart event. Regardless of what you select, though, the hardware that we use is the same. Our i3 Metal host is the host that we launched the service with. It's what we've had in production for the past 18 months. It has 8 1.74 terabyte NVMe SSDs locally inside the server. We take all 8 of those drives and we assign them to vSAN. We actually boot the server remotely off of an EBS volume. We take those 8 drives and we split them up into 2 disk groups. Now, we do 2 disk groups for a couple of different reasons. First and foremost, we get slightly better performance because we get multiple threads and the ability to run 2 D-stage parallel. But it also just makes for a more resilient storage system because any loss, if we were to lose an entire disk group, it's only half of the data that's on the host. So we'd only have to rebuild half of that data. All told, on top of this, this provides about 10.2 terabytes of physical capacity for every host that we add inside the cluster. We do enable deduplication and compression on top of that to amplify the usable capacity. And I'm going to get into what that looks like a little bit later on. We'll actually talk about what to expect from capacity as well as performance when we're looking at these hosts. We've recently expanded the service. Yes?
Why have you got encryption enabled and self-encrypting devices?
Yeah, great question. So why are we encrypting the data twice? So the self-encrypting NVMe SSDs are part of Amazon's lifecycle operations. So when we return a host to the AWS fleet, the way that we delete the data that's on that host is Amazon deletes the keys that it's using to read that data off the local NVMe SSDs. Now, that's great for Amazon, and it guarantees that your data is not going to be exposed to someone else who gets your host 20 minutes later. But that doesn't really help us if you have a compliance reason that's driving you to use data at rest encryption. Because more often than not, those compliance use cases, they carry key rollover requirements where you have to change out your keys at periodic intervals, and you also have to be able to prove that those actions happen, that you change those keys. So vSAN Datastore, data at rest encryption, it gives us those controls. It gives us the ability to actually get proper key management, be able to do key rotations as well as logging and monitoring of the data, and do that outside of the native self-encrypting NVMEs.
So that's pretty interesting. So what you're doing is, for some requirements where a customer couldn't necessarily get that from AWS, even though AWS are doing it, you're doing that and then actually enabling an additional service on top of the platform. So you could give those things to a customer in terms of the audit logs and showing those key rotations and those kind of pieces.
Yeah. The key rotations are logged inside the AWS KMS because we do use the AWS KMS by, well, not by default. It's hard linked to it. We don't support bring your own KMS at this point in time. We do that for availability purposes. As long as there's a single AZ alive inside the region, we'll be able to get our keys and access the data. But absolutely, yes, this was a case where we launched the service, we had self-encrypting drives, right? We had encryption at rest, and we found out through our customers. They brought their data, they brought their workload, they looked at it, and they said, actually, not good enough, try again. And we had to go back to the drawing board, and we found the answer we needed in vSAN data at rest encryption. Yes, sir?
Just a qualifying question. So since you use KMS, does that preclude the customer using customer key material in KMS?
Yeah, that is correct. So today, inside the VMware Cloud and AWS service, when you deploy an SDDC, we automatically configure data at rest encryption. We don't ask you, we just do it. And then if you don't care, you don't ever have to think about it again. It's just on, your data's protected, you're good. If at some later point in time you discover that one of your workloads has one of these requirements where you have to do key rotation, well, then you'll just happily discover that your SDDC is equipped and all the controls are there. It's a little bit different because it's a dual responsibility model. It's actually thrice. We've got 3 companies that have to be independently audited, monitored, and confirmed to be able to prove trust all the way up through the stack. But we have done that work and we can.
I'm sorry,
Yeah.
this may be a little bit off, but on the compliance vector from this, whose EULA applies, whose license applies? Because at least in the US, for US-based regions, AWS does not promise that it will not provide KMS keys that it owns. You may not know this.
Yeah, no, that's deeper than I'm
Okay,
prepared to
cool.
answer. I
No
can
problem.
look for you. I know who to ask, but I don't know off the top.
Yeah, no problem.
Okay, moving along. So for those storage dense use cases, right? So our existing i3 host, 10 terabytes per host. We can put 16 of those into a cluster, 160 terabytes raw, about 120 terabytes consumable. That's a lot of storage until you see how much data customers actually have, right? There's some customers where that's not even enough for them to tickle. If I have a 300 terabyte workload, I can't even look at that with the i3 metal host. So we needed to take a fresh look at how we could offer high density inside the AWS cloud. And one of the challenges with high density is availability, right? How are you going to deal with these faults? Because this is a highly volatile environment. Failure inside AWS is not a question. Failure inside that fleet is a reality. It happens all the time. The scale at which they deploy and the scale at which we manage. So you just have to deal with that. And when we looked at significantly increasing the amount of capacity that we put inside a host without significantly increasing the amount of network bandwidth, we needed a different way to manage data storage. And what we came up with is something that we call Elastic vSAN. It is first going to be available inside our R5 metal host, which is in preview now in 3 regions, and we are rapidly working to expand globally. This capability fuses that vSAN data management engine on top of Amazon's Elastic Block Store product. And what's neat about this is the way that it's implemented. As I mentioned earlier, like it actually looks as though when you deploy one of these hosts, if you go in there and click on disk management, you can see the individual devices, and they look as though they're local NVMe storage. But on the back end, through some proprietary technology that Amazon has developed, they're able to attach these actual Elastic Block Store volumes programmatically, right? So this gave us the ability to give the customer a programmatic SDDC where they could come in the front door and tell us how much capacity they want on a cluster when they deploy it. Now, currently we support 15 to 35 terabytes in 5 terabyte increments. And this has to be designated at cluster creation. So, if you think you're eventually going to want 35 terabytes per host, then you're going to want to designate that when you create your cluster, because we can't start with 15 and change it to 30 later. And this, we talked about this a little bit in the previous section, but this is where that roadmap starts to come in. We are actively working with Amazon to expand the foundationals that we're working with, as well as our own products, to be able to make it so that customers can incrementally add this capacity after the fact. Question?
So in a traditional cluster, right, we have a dependency on the network between nodes. So that's where our latency is going to be, right? But now we have network attached storage. So each of those steps cumulatively add up. So how does that impact measurable latency for workloads in this type of model?
Yeah, so I'm going to end this presentation with a look at performance specifically to answer that. The short version is, technically, the storage is not inside the box, but when I say proprietary, I mean proprietary. There is no element of this that is off the shelf, to include how it gets to the actual storage, right? So forget everything you know about remote storage. It doesn't apply in this instance. This is an Amazon derivative that we have fully embraced because it gave us the controls that we needed for customers.
Okay. And how are you going about meeting the performance requirements of the cache tier in this model? Is that done by scaling capacity?
Correct. Yeah, we scale that. We scale each cache volume that we attach to the cluster is scaled such that we get a guaranteed 160 megabits of throughput, 10,000 IOPS.
Okay.
Yes.
So that was going to be that relates to my question. You know, when you build an infrastructure on EBS yourself, you're concerned about queue length, IOPS, sizing, those kinds of things. Are you totally managing that?
Somewhat. I'm going to ask that we hold off the performance stuff until I get to. I'll show it to you and I'll explain it to you, and hopefully, if there's questions after that, we can get into the details. But I'll show you what we can expect. All right. We already actually touched on all of this. We store the hosts locally on the cluster. Now, I am going to expand on this one thing because this did create a bit of a challenge for us, right? When we store the virtual center server on the cluster that the customer workload's stored on, this created a bit of a challenge for us because vSAN out of the box, right? When you stand up your cluster, it's a single data store, and we're putting everything inside that data store. Now, we needed a way to separate the operations teams. We needed a way to put the VMware operations on one side and the customer operations on another side and give each side full permissions without having to rewrite a whole bunch of stuff. Our answer here was to just add logical data store support on top of vSAN. The analogy here, though, and this is important to understand, the analogy is like folders in a file system or OUs in Active Directory. These are not resource pools. They have absolutely nothing to do with capacity management. They have nothing to do with performance allocation. It's just a way for us to administratively put the customer workload in one bucket that they have full control of, enabling VADP-based backups. And then put the VMware infrastructure in a separate bucket such that the customer does not have the ability to shoot themselves in the foot. Okay? And that's basically the infrastructure. It's pretty simple. There's not a lot to it. From a storage aspect perspective, you don't really have to know anything about the basic hardware or how vSAN works or how we're going to construct the cluster to be effective at consuming the service, right? Because you just come in the front door, you tell us how many hosts you want, and then from there we handle it for you because we control all of the configuration on your behalf. So what does a customer have to worry about then? What is the scope of storage management inside this service? And the answer to that is policies. VM storage policy-based management. Policy-based management, in case there's anyone on the internet who's not familiar, because I'm pretty sure everyone in this room knows about it, is a declarative policy-based control plane for managing all of the data services inside vSAN. So our availability, our quality of service, stripe width, any of those advanced features that vSAN can do from a data management perspective, they're all controlled via policy. There is nothing that is actually locked inside at the cluster level. Anything that's cluster level is controlled by VMware. So when you're using the VMC service, the only thing you think about from a storage perspective are VM policies, because that's the extent of your controls. With that in mind, I'd like to quickly go through some of this because, again, this is the only thing that you need to be able to actually understand. And I think that there's some cool things in here to talk about because vSAN lets you think about storage in a way that traditional storage just doesn't. And whether or not it's better depends on your perspective and history where you come from. But this has been designed so that a virtualization administrator can easily pick up and manage storage without having to master 10 years of primitives and proprietary technologies and ways of doing business. Out of the box, vSAN empowers you to just say, you know what, I don't care about availability. This is a truly ephemeral workload. For every gig written, I want you to put a gig on the back end, and if you lose my data and the VM's gone forever, so be it. I don't care. Right? We give you that power from a workload basis. And these policies, since they can be assigned on a VM or VMDK basis, this means that you can have a single VM, you can have a VM that is highly available with a single VMDK on that VM that is not highly available for scratch space or workloads or something like that. It's a level of flexibility from a storage management perspective that you just don't see in traditional platforms. Now, if we want to be able to survive a failure, we need to actually ask it to configure redundancy. And the way that we do that by default is through our mirroring-based policies. We can see here that when we configure a single failure using our RAID 1 mirroring-based policy, what vSAN does is it creates 2 full copies of the data. So any writes, there's a little bit of write amplification that happens, right? Because any writes that come in on the front end, we're going to do 2 writes on the back end. But we use that additional component copy to accelerate reads. We'll actually load balance reads across both of them, so it's not wasted. And then more importantly, in the event of a failure, since we have a full copy of the data, there's no reduction in performance. Everything stays steady, everything is consistent. Now, if we want to be able to survive more than 2 failures, we of course could just request or configure a double failure protection using that RAID 1 mirroring policy. vSAN would respond by adding a component chunk and subsequent witness copy. We'd need at least 5 hosts to do so, but we could lose any 2 hosts and we would not have an availability problem. Now, as you can see though, our capacity consumption is starting to get a little bit out of control, right? If I configure a double failure protection with a RAID 1 mirroring policy, if I put 100 gigs in a virtual machine, I'm going to consume 300 gigs of capacity out of the cluster. Now, for some workloads, maybe we look at that and say, no, it's totally worth it. I'm willing to pay that. I don't want to think about performance. I just need this to be available, and it's mission critical. But if we had a workload where we were concerned with that, and we said, I just can't afford to spend that much capacity for this workload, we could instead configure our erasure coding policies. And the erasure coding, excuse me, the erasure coding policies, instead of using a raw-based mirroring subsystem to protect the data, they actually break up the data across 3 segments and then produce a 3/1 RAID 5 data set if we configure a single failure protection. This gives us the ability to protect from a single host failure using 75% less storage, right? Now, it's not free because the way that we protect it is with a parity copy, and that parity copy has to be maintained. So if we have just a simple update, there's a little bit of extra I/O on the back end to keep it up to date. And then also in the event of a failure, we would absolutely be missing data, right? So we would have to reconstitute that data using the parity copy, which would cause a little bit of additional latency. But the power to be able to, on demand, on a per workload basis, come in and decide, you know what? I want to take the bias of this workload from being performance biased, and I want to slide it over and be capacity biased. And do that on demand, non-disruptively as needed, is something that just isn't available elsewise. Finally, of course, if we want to, we can increase that data protection all the way up from a double failure protection. We would require 6 hosts to do so. A little note on double failure protection. When we have more than 6 hosts inside a single, or more than 6 of our I3 hosts inside a single availability zone, our SLA requires you to run a double failure protection. Because the likelihood of us encountering 2 failures, trying to recover from the first failure with 6 hosts inside an AWS cluster is more than 0, and we need to honor that. But from a workload perspective, all the flexibility is there. And then final note on policy-based management, because for me this is really the big takeaway and the reason why I think this is worth actually focusing on, even though it does require us to rethink how we manage storage in a little bit of a way, because we're moving closer to the workload, and in a lot of ways asking the VI admin to really think about, okay, for this virtual disk, what kind of data are you going to put here? What kind of workload? What kind of requirements do you have? Would you like to customize this? And the beauty of that is once you fully grok the policy-based management subsystem, it basically frees you from scale. Scale is no longer a concern. You don't have to think about it, right? The DevOps community came up with a really good equation for this many years ago that I just fell in love with. It's a really simple math equation. Complexity times scale equals skill. The way that it works, you take the complexity of the solution you're attempting to manage, you multiply it by the scale you're managing. That tells you how much skill you need to accomplish that. When you take a highly complex data management platform and you try to scale it, you need a PhD. You need an army of them. When you take a simple management paradigm and you scale it, anybody can do that. And that's the power of policy-based management. It takes what is a complex topic, storage, and it's an entire discipline of our industry, and it makes it something that a regular application administrator can be effective at managing inside the cloud. Okay, now this of course is not free, right? This flexibility of architecture is just a series of choices, and to ship is to choose, and to go down one path always carries consequences. In our case, this flexibility, the consequence of it is capacity management can be a little bit complex. Because unlike a traditional storage system that hides its overhead from you, right? It's hidden. You buy 100 terabytes of capacity, it hands you a 30 terabyte volume, and you just pretend that the other 60 isn't there. vSAN shows you the whole 100 and says, how do you want to use it, right? Do you want to go no redundancy? Well, then we can store X amount of data. And how much data we can store, again, depends on those policy configurations. configuration. So if we take our i3 metal host configuration, for example, assuming we set a site disaster tolerance of none inside that stretch cluster deployment, if we had an ephemeral workload, we could fit about 7.8 terabytes of data on that 10.2 terabytes of physical media. Once we apply the storage amplification, our projection for how much you're going to save with deduplication and compression, it should take it up to about 11.7 terabytes raw usable. Now, our standard workloads, of course, customers need data protection. So there we're looking at closer to 5 to 9 terabytes usable for each i3 metal host that we add into the cluster. Now, the R5 metal host is a little bit different because we've got that enhanced availability of the underlying EBS media, right? That's helping us out. That media is highly durable on top of the resiliency that vSAN is providing. So you'll notice that there isn't any failure to tolerate 2 on this slide, and that's because our SLA does not require it. Right? Regardless of how many hosts you have when you're using the R5 elastic vSAN, we only require an FTT of 1. But there's still the same storage amplification. So if we take a look at our erasure coding use case, all the way up at the big boy, 35 terabytes of physical capacity, that gives us about 19 terabytes usable once we account for scratch space, metadata overhead, et cetera, right at 26 terabytes once we add in the storage amplification factor. So quite a bit of capacity. Yes.
Is there an option for the failure to tolerate 2 on the R5 metal?
Yes, yeah. You can always configure FTT2, right? We don't restrict it. It's just we don't force it. Unlike with the i3 metal host, if you start off with a 4-host cluster, you could start with like RAID 5. Add host number 5, you're still RAID 5. When you add host number 6, you actually need to go to a RAID 6 policy to stay inside the.
I was interested on that point. So if you scale to that point, do you then automatically switch all of the VMs to that policy?
We don't, because we don't force the customer to keep their workload in compliance. If you want to run a workload that is not eligible for SLA credits, you are entitled to do that. This is vSphere. You choose what you want to do with it, right?
That's an interesting. So you scale and you need to add that extra host to that CPU, and when you go from that 5th to that 6th host, suddenly you're out of SLA compliance for all the other VMs on that existing cluster. And then if you want to switch so they're SLA compliant, then you're going to have to switch to a more or a less storage efficient policy to get them into compliance. So your storage utilization is going to increase.
Yeah, this gets back to that old conversation, right? No matter which road you go down, there's always a trade-off, right? There's always a counterbalance. There's always a thing you can look at and go, well, that's dumb. Why'd you choose that option? And this is where we get with this. The reality is it takes us X amount of time to be able to recover 10 terabytes of data from a host. And if we are in the middle of recovering one of those, the likelihood of us hitting a second one when we have more than 6 hosts in a single Amazon availability zone is more than 0. And again, there are a lot of choices, and we've got, man, this is debated internally. We've got a lot of roadmap items and things that we're looking at to try to improve this. But the reality is today we don't want to force customers down a path.
So how is the state of the system configuration tracked so that liability in an SLA situation can be determined? Is that done after the fact, or is there some way of keeping that up to date to show what the state of the system was during that?
Yeah, so it's after. As I understand it, and I'm going to add the disclaimer to this because I'm not an SLA expert. It is documented. It's on the internet. If you want to read it and you are an expert, feel free to interpret that. But as I understand it, it's per workload. And the way that this works is in the event that we have an actual breach where we exceed those availabilities, right? When it comes to assigning credits, figuring out how much we're going to credit you and not charge you for the consumption of those resources, it depends on how many virtual machines you didn't have access to that were eligible. But again, we should get with an expert on that. Okay, so very quickly, because I want to save time for the performance conversation and we're getting towards the end. How do we figure out when we use R5 versus i3? What does this really come down to? And the thing I really want to establish here is that it's not really a case of one versus the other, right? These are two very different architectures. But they're very different architectures because it took two very different solutions to be able to realize a production-ready vSphere environment inside Amazon's cloud without having to rewrite the rules a whole bunch. The reality is, out of the box, that R5 metal host just is more money. It's more expensive, and it's more expensive because we're getting more. We have more CPU, we have more memory, we have more storage. Now, if we're dealing with an entry-level cluster, that of course is not going to be terribly effective. But as you can see, since those i3 metal hosts, I can't add storage, right? I can't dynamically just increase my capacity. The only thing I can do is add an entire host to the cluster. And if I'm doing that solely for the purpose of storage, and I'm not using the compute or memory at all, that of course is a problem. So it is in those storage-dense use cases where we need more capacity than we do compute and resources that we'll see workloads kind of slide into that R5 metal use case. Now, together, what this does is it really opens up the entire world when it comes to the kinds of workloads that customers have and the kinds of problems they're trying to solve inside VMware Cloud. When we combine these two, our i3 metal host gives us that low latency HCI scalability, right? 17 all the way up to 120 terabytes of storage capacity. And then that R5 metal host is coming in to backfill those storage heavy use cases for us. So when we can, of course, there's more than just this, and as the intelligence in this room exposed way before I got to this slide, EBS is not the same as local NVMe storage. So what does performance look like when we compare these two? Well, our baseline sustained performance, and when I say sustained performance, what I mean is vSAN, of course, has a two-tier architecture. All writes initially land in our cache and then are destaged opportunistically as time allows. It is possible, of course, to drive writes to that cache tier faster than we can destage. And we will eventually get to a point where the writing is limited by our ability to destage, right? We'll have to destage a little bit of room so that we can make room for another write. We refer to that as our sustained performance. So what you're seeing represents the worst case, right? This is when we fully filled it up, and this is our destage. And when we compare that point inside the environment, we see that the R5 metal host is about 70% of what we report with the i3 metal. So very, very respectable from a baseline performance capability. And this is where we see it really start to shine, particularly with those large database workloads, things like that. Now, of course, where we can see the difference in these two is in the burst capacity. When we take a look at what it looks like from a burst performance capability, this is where that additional performance inside that local NVMe media really starts to shine. Because we did a ton of work with Elastic vSAN to make it simple for customers, to get to your point, to not have to think about this stuff, right? They just throw their workload up there and it just works. We've done the work for them. We did everything we can to vSAN so that it would just naturally eke as much out of that back end as humanly possible. Now, the realities are we are bumping up against the limits of EBS at this point, right? This is as much as the underlying platform can deliver. The next question that instantly comes in is, okay, well, you're using, what about like IOC? Why don't you just go to a better class of EBS? And the reality is we've looked at that, and the finances just don't, it's not there. It doesn't currently make financial sense to go down that route. We monitor that situation. If it ever changes, we'll change our mind on that. Now, when it comes to which one of these do I really need, we don't ask people to try to guess. We understand this is a complex problem. We have tools. Right? We ask people to use our tools. In the event of VMware Cloud, if you go to vmcsizer.vmware.com, you will find our public sizer. You can just plug in your workload, and we will pump out a sizing for you, telling you how much capacity you would like. We'll also add in rather a total cost of ownership compared to that to what it would look like if we were to deploy a example config with ready node config, for example.
So do you have latency figures? Because IO is great and everything, but I really want to know latency for my workloads.
No, I understand.
That's more
so this testing was all normalized at the same latency point. So I understand your point, and this is those fine details of talking about performance on a live stream on the internet.
Yep.
And we can show that, but this is just to show relative. The latency here was within application tolerance, though. I'm not showing you 20 milliseconds, right? This is expected performance from a storage platform, and that's the whole point of this, right? And that's why we make this transparent, right? This is a 70% read working set, or 800 gig working set, 70% read, 16K IO, and with that back end, this is what we can drive on the front end. All right, very quickly, because I'm at the end of my time, I just want to expose that, we talked about a lot today. We talked about our direct attached NVMe storage with the i3 metal host. We talked a lot about the new capabilities that we're adding with the R5 metal host and elastic vSAN. But we acknowledge that storage is a big thing, right? We think that vSAN is the right answer for the majority of customer workloads that are coming into the VMware Cloud and AWS service, but there are different options out there, and we want to empower customers to use them. The storage industry is going through a bit of a revolution at the moment where many vendors are making it so that their products are available as an IaaS, PaaS, or SaaS platform, in a lot of cases adjacent in the cloud. We want to empower customers to leverage those other options in conjunction with their VMware Cloud and AWS SCDC. And that's where this managed data store support is coming in. We actually talked about this on a cloud field day last year at VMworld, so if you want more detail on that, just go take a look. We co-presented with NetApp for more detail on that. But the Elastic vSAN is currently in preview in 3 regions, rapidly working to roll out worldwide, and that direct attached i3 metal host is available worldwide today. And with that, for more information, be sure to check out our slew of resources that we have for you. And I hope you found this informative. Thank you very much for your time.